afternoon. I need to give myself a lesson in PIC programming, and I won't say much more. So I did some Google searching, and I thought I'd read this. The first set of tutorials on a different website I found was very poorly written, and I had to abandon reading it because it was just so hard to read. So hopefully this will serve as a better tutorial. So all credit goes to Khaled Magdi. So thank you very much. Introduction to Microchip PIC MCUs Programming Tutorials. And I'd just like to say that even though this appears on my channel, it's just for informational and educational purposes. I'm not trying to take the content, and I don't really care if my channel becomes popular, so just thought I'd say that. Hello and welcome to the Embedded Systems course with Microchip PIC microcontrollers. This series of tutorials is dedicated to teaching you the basics of embedded systems development using the Microchip PIC MCUs as a platform for practical experimentations. In this series, you'll start learning the very basic concepts in PIC microcontroller programming to the advanced ones. However, there are some prerequisites indicated below that are assumed to be fulfilled. Well, you can jump straight to the TOC, table of contents, at the end of this post. But I encourage you to read the following sections just to make sure that these tutorials are going to be beneficial for you. Prerequisites. While creating these materials, I assumed some basic knowledge in some areas are already existent and well covered by all of you. The assumed basic knowledge includes basic circuits and electronics knowledge, circuit analysis, laws, resistors, diodes, transistors, etc., digital electronics fundamentals, numbering systems, logic gates, etc., basics of C programming language, data types, operators, flow control, functions, etc. However, many of these topics may be presented and developed from the scratch occasionally, but this is not always the case, so it's highly recommended to have the basic background in each of these areas anyway before starting any sort of embedded systems training. Note, anyway, these are just my recommendations for all. Obviously, you could start right away and make sure to ask about whatever you see is an ambiguous or unclear concept. Target audience. Okay, this is great information, but I'm going to skip it. Okay, I skipped a little bit of content. I'll read the last sentence. That's why you should not care too much about which platform to learn first. Example, AVR, PIC, Arduino, ARM, or whatever. It's not a big deal. Here I will explain why one may go with the Microchip PIC option and give it a shot. Engineers do more with less. Is it a good idea to learn PIC MCUs nowadays? Is it still used at the production level? Is it worthy anyway? Shouldn't I go for the Arduino or Raspberry Pi or any fancy stuff around there? Well, I will put all these questions and others to an end. I hope to clarify everything you may be wondering about, but first let me tell you a real-life example story. I skipped a bit of information. Technology platform's brand, example AVR, Arduino, PIC, ARM, etc., has nothing to do with the underlying fundamental concepts that technically drive these machines, which you'll be learning in this route. And that's why you shouldn't abandon what others describe as obsolete, just only for the sake of it. It's amazing how much you learn when you play around with moderately old machines, as long as they have concise, clear documentation. Microchip versus prototyping platforms. Well, it's really recommended that you go for an Arduino or Raspberry Pi or whatever prototyping platform in case you aren't pursuing a firmware career. But if you're willing to work in the embedded industry as a firmware engineer, then but if you're willing to work in the embedded industry as a firmware engineer, then invoking pre-built Arduino functions, sketches, and libraries will take you nowhere further. However, these tools can be used in a very effective way. It's only if you're building everything from scratch yourself. And yes, reinvent the wheel. Please just do it. A very basic platform will give you the chance to understand the underlying concepts and mechanics of the low-level hardware, and of course to develop your own libraries, drivers, and so on. This is what enhances your embedded software career in the long run. Microchip PIC versus production-level platforms. There is nothing could be compared to the ARM-based devices in the embedded market in terms of performance. Okay, so I guess ARM-based devices have the best performance, okay? However, some other platforms from other manufacturers are being shipped and used in many situations, but obviously not comparable to the 30-bit ARM cores, specifically in the high-end devices. That's why you must consider learning ARM programming and interfacing at some point in your path. There's no doubt that a 32-bit MCU delivers higher performance than an 8-bit device, but the engineer faces the traditional decision of choosing between the best available device in the market versus an application's actual needs. Here is an old forecast back in 2014 which confirms all 8-bit MCUs have the lion's share of the embedded systems market in terms of shipments and revenue in $1 million. Okay, up until 2017, the 8-bit MCUs are slightly ahead. Note that this is an old forecast and the numbers are a bit changed, but you've got the point of it. Since the 8-bit MCUs cost substantially less, their actual numbers still far exceed the 32-bit devices, and Microchip is the leading producer of 8-bit microcontrollers, PIC plus AVR. On the other hand, a typical datasheet for an ARM core may be in the 1500 pages long range. Yes, it's more complicated than AVR, PIC, and other platforms. That's why a beginner should start with a much simpler platform from Microchip that may have about 200 pages datasheet. The bottom line. Every single microcontroller has some sort of input-output ports with serial parallel communication. Peripherals, internal, external memory, interfaces, interrupt circuitry, and some extra peripherals and features, all of which operate similarly on all platforms anyway. Actually, timers, USART, I2C, SPI, and other peripherals are the same things whether you're using a PIC or AVR. Who cares? If you are familiar with one platform, you'll find it easy to translate your experience to another one, maybe an ARM, AVR, or whatever. Just take the time and effort to master a single platform, then moving to another will be a matter of few days flipping through its datasheet. Note, the process of translating your coding files, projects, or so from one platform to another is called porting. If you're still wondering if X microcontroller is still used in the industry or not, then the answer is yes. If the manufacturer is still supporting and producing that device, there should be a market for it. There is a microcontroller for every situation. Aggressively pushing an energy-hungry 32-bit high-end core in any embedded device is not as much efficient as it seems to be. There are countless situations where preserving the battery life is the #1 priority. Required hardware kit. Here is a brief of the hardware development kit we'll be using through this series of tutorials. MCUs. So it's got the PIC 16F877A, sensors, ultrasonic, modules, interfaces, relays. Okay, so sensors, ultrasonic, temperature, pressure, IMU. I guess they correspond to the microcontroller units. Modules, relays, LCD, USB, TTL, Bluetooth, actuators, DC motors, stepper motors, servo motors, speakers. This is actually a non-exhaustive list to only give you an idea about what we'll be doing through these tutorials. Which MCUs we'll be using specifically. In most cases, it's going to be the classic PIC 16F8778 chip. You'll find the Expressful course kit components and their quantities all listed down in the resources page associated to this course. Just click the link down below. Required software tools, free. There exist several software tool chains that are being used for developing embedded C project with the Microchip PIC MCUs. Many of them are paid services, and there exist some pirated versions for them, but we'll stay away from all these stuff. We will be using the original free tools from Microchip, which is the supplier of PIC's MCUs as well. IDE is MPLAB IDE, any version. The compiler is the XC8, any version. Simulator, Proteus ISIS, any version. Flasher depends on your hardware programmer kit. I use PIC 2 and 3. The download links and installation instructions are all discussed in detail within the following tutorial. The list above is for identification purposes. Table of contents. Below is the numbered table of contents for this series of tutorials. It'll be consistently updated for new publications. Alright, well, there's a nice list of different articles that you can click on and read, and it goes down into like more advanced interfacing. So I'll click on the Introduction to Microcontrollers. I did it. This popped up. Microcontroller Programming Introductory Tutorial. In this tutorial, you'll get to know what are microcontrollers, what's inside a typical MCU chip, how does a microcontroller actually operate, set everything up and become familiar with the development environment or the Microchip PIC microcontrollers ecosystem, which we'll be using through this series of tutorials. Introduction to Microcontrollers. As we stated earlier, an embedded system is a computerized system that in most cases will not look like a computer. We've also mentioned numerous examples of embedded devices and devices applications. The computers being embedded in these devices are small microcontrollers, MCUs, or also abbreviated as Micro C. Sorry. You should also know that microcontrollers are not the only option out there for embedded solutions devices, but MCUs are our main interest in this series of tutorials. Now we'll consider one of the previous embedded devices examples to have a closer look at its main components. Let's consider the drone, for example. A typical drone will have an internal structure shown in the diagram below. So it has a battery, I guess for whatever reason it's called ESC. There's 1, 2, 3, and 4. Well, what's an ESC? I don't know. Maybe he'll get to explaining it. Wi-Fi, UART, I2C, a PWM signal, UART, I2C, SPI, USB, a camera, memory, a compass, RF, GPS, IMU. Well, this aerial robot consists of some mechanical and electrical parts. We're only concerned with the electronic embedded system, which has the following components. Camera, electronic sensor used for imaging and video recording. GPS, the sensor is used to get the coordinates information of the vehicle at any instance of time, widely used for locomotion tasks. IMU, an IMU is an inertial measurement unit. It's typically used to get information about the static dynamic properties of the vehicle, such as angular rates, tilt, angle, and acceleration in 3 axes, in order to keep its balance and plan for smooth maneuvering. Compass. This sensor is used to measure the heading angle of the vehicle, which is very helpful for controlling its orientational motion. Modules. Wi-Fi. This module adds a Wi-Fi internet connectivity to the vehicle used for control or data transfer. Modules, RF. This modules adds a radio frequency connectivity to the vehicle used for communicating with the control station. External memory, onboard additional memory for data and setting storage. Drivers circuitry, ESCs. Electronic speed controllers. These electronic circuits are pre-built and packaged devices that are being sold as an electronic driver solution used for brushless motors. Actuators, 4 times brushless motors. These are the actuators that cause motion for this vehicle. DC power source, batteries. The rechargeable power source used for drones. It's the bottleneck of the whole system, which can definitely tell for how long can this machine fly in the air. Central computer, microcontroller. This is the brain of the system that handles all computations implemented in the control system mathematical model. It also interfaces with all sensors to collect all the needed data for a robust controlled behavior, and also communicates with the operator, you, via the RF module to pass your commands to the vehicle, which will follow them. There is no doubt that the micro C, or the embedded computer, is the most important part of these components, as it handles almost everything. A typical sensor or actuator may possibly have a datasheet associated with it that can take no longer than 10 pages. On the other hand, a very simple microcontroller will typically have a datasheet that is no less than 100 pages long. In fact, most MCUs chips have datasheets that are between 200 to 2,000 pages long. Each module within these small chips can have a documentation that is 25 pages long on average. That's why in the following tutorials we'll be more focused on the microcontroller programming, and we'll discuss each of the modules in detail to understand the underlying mechanics. However, we'll also be interfacing many of the common modules and sensors on our way through. We'll do our best to balance between understanding all the MCU's modules in detail and practically interface some sensors, actuators to create small projects. So stick with me, it's going to be tough indeed, but it's really worth it and definitely rewarding. What is a microcontroller? A microcontroller is a single-chip, self-contained computer which incorporates all the basic components of a personal computer on a smaller scale. Microcontrollers are typically used as embedded controllers that control some parts of a larger system, such as mobile robots, computers, or computer peripherals, etc. A microcontroller is fundamentally a smaller version of your personal computer. It has the same exact component, but with limited capabilities and resources. An arbitrarily made comparison between X computer and Y MCU may result in a table that looks like the one below. RAM. A computer has 1 to 8 gigabytes. The microcontroller has 128 bytes or 512 kilobytes. ROM has a few megabytes, 4 to 46 kilobytes. Clock rate 1 to 4 gigahertz, 32 kilohertz to 200 megahertz. CPU cores up to 16. Microcontroller 1. Serial ports, USB, thus UART, SPI, I2C, and USB. Current drain 1.5 amps, 50 milliamps. A microcontroller is not the same as a microprocessor. A microprocessor is a single-chip CPU used within other computer systems, while a microcontroller is itself a single-chip full computer system. We use microcontrollers extensively in embedded systems design. You can spot its existence in a tremendous number of applications and devices around you. A microcontroller can possibly show a higher efficiency and performance in some sort of applications than any computer we use. When it comes to low-end devices and minimal power utilization, there is nothing comparable with microcontrollers. It drains a few milliamperes that will result in a substantial increase in the device's battery life. Variants of microcontrollers. Microcontrollers, this picture is distracting. Variants of microcontrollers. Microcontrollers can be categorized in many different ways depending on numerous metrics. They could be categorized based on their memory, architecture, bus width, CPU architecture, manufacturer, and so on. Here I will list down some of these categories, and finally we'll tell you which MCU chips we'll be using in these tutorials and why. Bus width. The bus width, number of wires, determines the capability of the computer to handle data, words of a specific length. An X bits microcontroller can manipulate data up to X bits in size. However, there are many MCUs that have a full instruction set that handles 8-bit data alongside with a few ones for handling 16-bit words. In this case, it should be called an 8-bit machine. A specific microcontroller is considered as an X-bit computer if it has an instruction set that most of its instructions are designed to manipulate data words of X bits size. The 8-bit microcontrollers are the most common with the highest shipping volume in the market. However, there are 16-bit and 32-bit microcontrollers that are used for high-performance applications that require excessive computational power. In conclusion, the microcontrollers market standards and bus widths are the three ones listed below: 8-bit micro Cs, 16-bit micro Cs, and 32-bit microcontrollers. Memory type. Microcontrollers' memory may be embedded within the chip itself, or the chip could be designed to operate using an external memory hooked to the microcontroller chip externally. Internal memory MCUs. These devices are designed with all needed RAM and ROM memories built in. There is no need for any external connections for memory. This represents the majority of MCUs being manufactured nowadays. External memory MCUs. In the past, some chips had no program memory built in, and they had to connect it externally. That's what happened with Intel's 4004 MPUs back in the late 60s. This type of MCU had to disappear with the emergence of internal memory designs only 5 years later, back in 1975. Instruction set. Every single microprocessor has its own instruction set which defines the basic function it only can handles. And some editing. Every single microprocessor has its own instruction set which defines the basic function it only can handles. I don't understand that. Some sophisticated functions could be achieved using the basic instructions available in the instruction set of a microprocessor. Here is an example of a set of assembly instructions that could be found in any device out there. The function it performs. Name add. Adds two operands together. Sub. Subtracts two operands. Mul. Multiplies two operands. Okay, and so on and so forth. Let's consider a microcontroller which has a very basic instruction set that does not include the modulus percentage operation, which returns the remainder of the division.